In this video, we will learn about one of the very special types of functions, which are the recursive function. Recursion is a very fundamental topic in computer science. I have to warn you that this is one of the hardest topics that you will encounter during programming. Not during this course. I'm trying to keep this section as a simple one. I will try to use very simple examples here in the explanation in the homework. But I would like to tell you in general, recursive functions are hard. They take a lot of time so that you can understand really them. During the algorithms course, you will encounter several types of algorithms that are dependent on recursion. And the more you go with all of these topics and problem solving in algorithmic course, you will be better and better in recursion. So my advice for you in this section, give it a very good trial. Eventually, like a couple of years from now, you will realize that the examples that are explained here are very basic examples. Meanwhile, they are going to take some time from you to get them. So take it easy. Recursion is really very tough for almost everyone. Let's first try to introduce the idea. Let's think about decomposition. Sometimes when you meet a big problem, you try to decompose it to a small sub-problems. Then it is easier for you when you tackle the sub-problems than try to solve the big problem itself. Let's give an example. Let's print all numbers that are both prime and palindrome in the range of 1 million. So we have here like two sub-problems, prime numbers and palindromes. A prime number is a number, as we know, that isn't divided by a number less than it except 1. And palindrome is something that you can read from the left as same as the right. Now, if you manage to solve these two sub-problems, you can simply iterate from 1 to 1 million, and then if a number satisfies the two conditions, then we are going to print it. That's all done. Now, what if the sub-problem is the same type as the problem itself? The sub-problem is same as the problem itself. We call this recursion. So sometimes the problem is divided to a set of sub-problems of different type, but the tricky case when the problem is divided to sub-problems of the same type. So let's go in details. Consider the factorial, for example. Factorial 6 is a multiplication of the numbers from 1 to 6. Factorial 5 is the multiplication of the numbers from 1 to 5, and so on. I would like you to think for a few minutes. What is the relationship between factorial 6 and factorial 5? Also, if you know can we know factorial 6 if we know the answer of factorial 5 or not? Give yourself to think for a few minutes and consider what I was saying about the problems and sub-problems. We definitely can implement the factorial in a very simple way. We can just iterate and multiply all of the numbers from 1 to n, and that's it, with such a very simple function. Observe here. Something like factorial 5 is a multiplication of the numbers from 1 to 5. Factorial 4 is a multiplication of the numbers from 1 to 4. If you know factorial 4 results and just multiplied it with 5, you actually get the result of factorial 5 itself. In a similar way, factorial 6 is a multiplication of the numbers from 1 to 6. If you know the answer of factorial 5, which is 120, and multiplied that result with 6, you get 720. With this logic, it seems there is a clear relationship between factorial 6 and factorial 5. First of all, both of them are the factorial problem. Factorial 6 is a problem, but you can think of factorial 5 as a sub-problem, but it is now one less harder. So if you have the factorial 5, you can multiply it with 6 to get factorial 6. If you have factorial 4 and multiply it with 5, you get the factorial 5. If you have factorial 3 and multiply it with 4, you get the factorial 4. I hope you now here realize what we mean, that the problem can be solved using a smaller sub-problem of the same type. So factorial 6 is going to use factorial 5, which is of the same type. So this is mainly what we meant here by problem and sub-problem of the same type. But there is one interesting question here. Are we going to end that forever? Like factorial 6 need factorial 5. Factorial 5 needs factorial 4, which needs factorial 3. Are we going forever? No. We stop at something we call the base case. The best case is something in the very end of this sequence that we already know the answer for it, so there is no need to keep going down in this track. And when you think about something like factorial 0 or factorial 1, we know that the answer already is 1. So factorial 1 or factorial 0 doesn't need to keep going down to less and less a smaller subproblem. Here is a way to implement that in a bit like a weird way. I'm defining 6 functions: factorial 1, factorial 2, factorial 3, factorial 4, factorial 5, and factorial 6. Each one of them is returning the answer of factorial. Let's say that factorial 4 is going to return the result of factorial 4, regardless of how is it computed. Now factorial 5 is simply the factorial 4 answer times the 5. In a similar way, factorial 6 is the answer of factorial 5 times 6. Factorial 1 is our base case. There are no more subproblems, okay? Maybe if you'd like to, in case you would like to handle the 0 in a professional way, you can also add the factorial 0 here as a case. I hope you got the sense of a problem and a subproblem. In the next video, we will see how this code can be written with only a single function that is actually calling itself rather than calling another variant of the function.